And so now that we have looked at stoichiometry and we've looked at types of chemical reactions and driving mechanisms of chemical reactions such as metathesis and reduction oxidation, what we're going to do now is we're going to look at the most common way that reactions, especially in first year chemistry, are going to occur. And we refer to this as aqueous solutions. So this is aqueous solutions in chemistry or aqueous solutions stoichiometry. You can already see where this is going. And so one of the things that students usually struggle with when we move into this idea of an aqueous solution is that a student will see a liquid, right? So for example, I might give you a solution of sodium chloride. And the misunderstanding that students immediately run into is that they tell me that the sodium chloride is in a liquid state, right? Couldn't be further from the truth. What we're going to be looking at in this section is that when we talk about aqueous solutions, we're going to be referring to another state of matter. So if you recall, when we looked at our states of matter, we had our three common ones that we all know. So we had, of course, our solids, our liquids, and our gases, right? And then I said there's another state of matter that we want to have an awareness of, and this is the idea known as an aqueous, AQ, right? An aqueous solution. So the question that usually comes up when we talk about aqueous solutions is what is different about an aqueous solution versus a solid, liquid, or a gas? And recall, this goes all the way back to the beginning of the year, that when we talk about solids, liquids, and gases, those are going to be pure substances. In other words, that is going to be either a single type of element or a single type of molecule. However, when we talk about a solution by definition is a mixture. And when we talk about aqueous solutions, to be more specific, the word aqueous means in water. So what's happening is that water is the solvent, the thing that's doing the dissolving, and then the other substance is the solute, the thing that is actually getting dissolved. Now, why is it so important to have this distinction? Well, because when a substance, and I'm going to put air quotes on this, when a substance dissolves, what happens is that it is going to break up into smaller pieces. Now, how it breaks up into smaller pieces is what we're now going to start talking about, because what we notice with most solutions is that solutions can usually be classified as an electrolytic or as an electrolyte solution or a non-electrolyte solution. And that's a fancy way of saying when you talk about electrolytes is are ions present? To say it a different way, it would be to say that did the substance disassociate versus did the substance dissolve? So, okay, we got a lot of words here. Let's see how we can kind of unpack these words and say something intelligent about all of this. So, let's start off with an electrolyte. An electrolyte is any solution that can conduct an electrical current, right? In order to do so, ions must be present. Now, what happens if a lot of ions are present? Well, my guess is that then the solution is going to be really good at conducting an electrical current. Or, to put that a different way, we could say that the solution is going to be a very strong electrolyte. Cool. Well, what happens if a substance only breaks up a little bit into ions? Does that mean it can't carry an electrical current? No, it can still carry an electrical current, but it's now going to be something that we'll refer to as a weak electrolyte. In other words, it can carry a charge, but not the best. Now, the idea of to what extent does the solid break up, right? In other words, how many ions get produced, that we'll deal with more later on in the year, and more importantly, that's what's going to then determine whether it's a strong or weak electrolyte, the amount of ions that we produce. So, if in order to be an electrolyte we have to create ions, then the question is, well, why distinguish between the word disassociate versus the word dissolve? And this is an important point that you want to make sure you're clear about. When a substance disassociates, what happens is that it is going to form separate ions. So therefore, in order to dissociate, what we're saying is that the substance is now breaking apart. And it's breaking apart into the original cations and anions that made it up. So to dissociate for an ionic compound means to break up into ions. When an ionic compound, again, air quotes, dissolves in water, it's not that it's breaking up into smaller pieces of the same substance. What we're saying is that it's now breaking up into separate ions. So think we're going to have a bunch of new cations in the solution. We're going to have a bunch of new anions in the solution. So let's take a look at how this plays out at the molecular level. So what I've done here, again, my amazing artistic rendition, I've drawn a molecule of sodium chloride. So let's just take something simple. This is good old-fashioned table salt. And what you'll notice is that when I have a molecule of sodium chloride, we have the smaller sodium ion. That's going to be the one in yellow over here. And then we have the larger chloride ion, okay, or the chloride anion. That's the bigger one over here. Now what's going to happen is that in order to make a solution, what I'm going to do is I'm going to take my little beaker, and in my beaker that was full of a bunch of water, so there's nothing but H2O in here, right? I'm now going to add my little pile of NaCl. Boop, right? So here's my pile of NaCl. And so the question then is, when I put the sodium chloride in to my pile, what is going to happen? What are we going to see? And what's going to occur is that the sodium chloride is going to start to get surrounded by the H2O. Now you might recall, maybe from your biology days, maybe from your middle school days, somewhere along those lines, you might recall that water was a very special and unique molecule. We refer to it often as the universal solvent, whatever on earth that means, but what you may have heard, and again we'll speak more about this later on, but what you may have heard is that water is a polar molecule. So what do we mean by water as a polar molecule? Now, for reasons that we're not going to get into right now, we'll just say magic at the moment. Water tends to have one side slightly more negative and the other side slightly more positive. So when we look at water, water is still a neutral molecule. It doesn't have a particular charge. But if I look closely, I would notice that the side with the oxygen seems to have more electrons around it, okay? The side with the hydrogens seem to have their nucleus seem to be more exposed. Now, all that means, like I said, to keep it simple for right now, is that water doesn't have an even distribution of its electrons. So one side, the oxygen side, a little negative, a little bit. The hydrogen side, little positive. How does all of this play out? Well, let's now create, over here on my left-hand side, let's now create a grouping of sodium chloride molecules. And what you'll notice with my sodium chloride is that all of them are set up in such a way so that if you look closely at this, let me actually make this a little bigger so we can see what's happening here. If you look closely at this, what you'll notice is that my sodium chloride is set up in such a way that we have a positive, this is my sodium ion, and then a negative, this is my chloride ion, and then positive and negative and positive and negative, right? But the next row down, what you now notice is that it's like the sodium chloride kind of flipped itself around. So if this guy originally was Na and this guy was originally Cl, in the second line we see that this is my negative and this is my positive, or this is my Cl and this is my Na. Right? Now, why do I emphasize this? Why is it, do I make sure that you see it? Well, what we are noticing is that my structure is set up in such a way that I have my ions attracting one another, kind of like magnets on your refrigerator do. So if you recall, like repels like, but opposites attract. So what we're going to see here is a positive is hooking up with a negative. So when I come over here to my molecule of sodium chloride, what I'm now going to do is I'm now going to have water molecules begin to attack it. But what you're going to notice is that everywhere where there's a sodium, we're going to see the negative side of the water start to approach it. And so I'm going to have that happen over here, right? And I'm going to have that happen, let's put it way out over here. And just like I have the water, the negative side of the water attacking my positive sodium ions, well, when you have the negative side of the chloride, you're going to see that the water is going to attack this as well. But now notice how the water reverses its positioning, right? And so it kind of flips itself around so that the positive side, the hydrogens, begin to approach or attack each individual chloride ion. As a result, what we end up seeing is that when my sodium and my chloride get pulled apart, we're actually going to see the sodium and chloride ion now separated and surrounded by a bunch of water molecules. So in my act of disassociating, what we notice is that my Na, my little Na that was here, and my Cl, my big Cl that was next to it, when the water came into play, it went, and in doing so, it now has cleaved the molecule and separated it as two distinctive ions. This is what to disassociate means. So it's no longer NaCl together, it's now Na and Cl, better said as sodium ion and chloride ion, separated. So then the question becomes, well, if that's what's happening when something disassociates, what really is occurring when something dissolves? And so in dissolution, or when something is dissolving, what we're going to see is that we're going to break a big structure into smaller and smaller and smaller pieces, but that are still the same. In other words, when something dissolves, we're not cleaving molecules, we're not separating ions, no ions are present, and everything stays as a neutral compound. Typically, molecular compounds, those are nonmetal with nonmetal compounds, are the ones that we will say dissolve, especially in water. So to kind of give us an idea of this, what we're going to do is we're now going to look at sucrose, better known to you and I as a sugar molecule. So what you're going to see here on the left-hand side is I put a bunch of sucrose molecules together. And sucrose is going to be C12H22O11. If you want to use a simpler sugar like glucose, C6H12O6, same thing, tomato, tomato. But what happens, what you're going to notice is over there on the left-hand side, all of my sugar molecules are packed closely together. Right? Now, for reasons that we're going to call magic right now, there's some forces that keep those sugar molecules combined and joined together. They're intermolecular forces. We'll see them later. But when the water comes into play, the water can actually get between the individual sucrose molecules, or in between the individual sugar molecules. It can overcome those forces, and as it does that, it now literally separates each of my sugar molecules into individual molecules separate from one another. The result is that we would see my nice block of sugar disappear. We would say that the sugar has dissolved, but I would say that it has dissolved because it's still, every single molecule is going to be my original C12H22O11. It doesn't alter the molecule itself. And so it is this distinction between dissolution and disassociating, right? So to dissolve versus to disassociate. It's this distinction that then will allow us to identify whether a compound is breaking up into separate ions, like it does when something disassociates, versus it's just breaking up into more of the same but smaller and smaller little pieces of it, all still identical, as you see when something dissolves. That then brings us back to where we started, which is in order to create an electrolytic solution, we need a lot of ions present. So we need a substance that is going to disassociate to a very large extent. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.